Sure, you can do it. What you got to do? Because now we're recording this, and so you can watch this part of the video later. Go, get out of here right now. Okay, we had I have my mic on. Okay, hey, it's physical science time. Oh, I'm sorry, we forgot to bubble. What was our answer here? I'm gonna bubble it. No, we're trying to have a video.
Bubble it. Oh, that's
63. You can bubble at a different time. Okay, so we had some equations. You can probably still see them. I'm gonna make it picture in picture so you can see them real quick. We have some example equations. If you need to go back over these, you can. They're already erased, half of them, but that's not the point. That's not what we're doing today. What is the title of this lesson? We've had it up here yesterday. I didn't get to it. What is the title of this lesson? Gas laws. So let's write that down. There are at least 5 commonly used gas laws in chemistry. We're going to talk about 3 of them today as physical science students. This is as I had said before, this is the beginning of our unit on chemistry. So this is one of the things that we do that you will do again, but in more depth in Chem 1. So each of these 3 gas laws we're going to talk about today relate these 3 quantities. So let's write down these quantities. We have temperature. Do you have questions about what temperature is? We covered this in chapter 5. Do you have questions about what temperature is scientifically?
weather.
No. That's worrying to me. We're talking about temperature. Do you have questions? Yeah, it's the average kinetic energy of the particles. Do you have questions about what pressure is? We talked about that yesterday, and we did some problems with it. Do you have questions about what pressure is? Pressure is force divided by area. It's the amount of, it's not just the force exerted by something, it's the pressure exerted by it. A classic example of this is that if I put the same amount of force, if I have a assistant, can someone be the assistant? Just come on screen, but just your arm. Gunnar, come over here, just your arm. I'll tell you when to stop. Stand right in front of this. No, it isn't. Just his arm. Just his arm. Oh, okay, that's good. If I have just disembodied arm, and I have 2 things here. I have coffee cup, which has coffee in it, so be careful. And I have pen. I'm going to put the same force on Gunnar's arm. Resist me. I'm going to put the same force on Gunnar's arm with both of them. I'm going to not open the pen so you don't get your hoodie ruined. Did it feel different?
Yeah.
Yeah, it felt different. But I put the same force on both. What was the difference?
How do you know you put the same force?
Oh, I guessed. Yeah, the smaller area of the pin. So there's a greater pressure. That's why, thank you, go sit down. Give him a round of applause real quick. That's why if you're in a situation like commonly happens to all of us, and you're in a truck stop, and a trucker says he's going to step on you, and he makes you pick whether he's going to wear his hiking boots or his high heels, you want to pick the hiking boots, because the high heels have a smaller area, so they'll exert more pressure, and that'll go into your gallbladder, whereas the hiking boots might just kind of like give you a bruise on your back. You know, this common situation that we all have. Okay, so that's what pressure is. What the other quantity that we talk about in the gas laws is volume. Hey, where's Chloe? I need my balloon and the balloon blower upper again, please.
Can I please do it one day? Just one time.
You want to go get the balloon?
Yes.
You can go with her. So we have these 3 quantities that we know about already, right? Right?
Yeah.
We're going to label them capital T is temperature. By the way, what's lowercase t in a science equation? Time. So capital T is temperature, capital P is pressure, capital V is volume. Those are not difficult symbols to remember. We have 3, as I said, gas laws. Let's name them now. We have, in fact, I think your book might only talk about 2. We're going to talk about 3. Your book only talks about 2. We have Boyle's law, Charles's law. I have a little side note here. If you pronounce a word that ends with S when you use the possessive like we're using here, whose law is it? Yeah, it's Charles's law. If you say that as, which is fine, either way is fine, we agree in English. If you say Charles' law, like the man's name is Charles, but when you give him the possessive, you also say Charles' law, just put the apostrophe after the S. But if you, like I, say Charles's law, put another S at the end. Like if you're talking about our Lord Jesus and you say Jesus' blood, and that's how you say it, you put the apostrophe after the S. But if you say Jesus's blood, you put the apostrophe and then another S. Doesn't really matter. Whichever way you say it, you should write it that way. For some words it does matter, I'm sure. I can't think of any. So Boyle's law, Charles's law, and now we have the third one, which is from a French guy named Gay-Lussac. So don't make fun of his name. He can't help it, and he's also dead. But these are the law. Boyle's law, Charles's law, Gay-Lussac's law, and those relate. We're also going to talk about, the combined gas law, because that'll make it easier. These four, well, really three, and then the combined one is like their stepchild. But these three laws relate these three things. And if I had my balloon, I would show you a demonstration of that. But the way you can remember, this is the way I remember, which maybe, if you're thinking of a better way, first, use it. Second, please tell me, because this way is not very good. The way I remember Boyle's law is because Boyle sounds like it should be hot, like boiling water, but it has nothing to do with the temperature. It's the one that has nothing to do with temperature. It is when pressure on a, hey, what do these all have to do with probably? What state of matter are these all about? Gas. When pressure on a gas increases, its volume, can you guess? If I squeeze harder on a gas, what probably happens to its...
Balloon gone.
Oh, what?
Balloon gone.
No. Okay, well, glove will work, thank you. I believe you. It decreases, yeah. When pressure on a gas increases, its volume decreases. Tell me, what kind of proportional are these?
Small.
Think about it, and then raise your hand, and then say the right answer, someone, please. What kind of relationship is this? Hunter? So we had pressure increases, volume decreases. Raise your hand if you know what kind of proportionality that is.
Inverse.
No, raise your hand, Will.
Inverse.
Inverse. They're inversely related. As one goes up, the other gets down. The equation for this is P1 V1 equals P2 V2. These little subscript numbers mean what, probably, if you had to guess? Are we talking about the same pressure and the same pressure? No, because they're labeled differently. It's actually, the way we usually use this is before and after. Pressure in time 1, pressure in time 2. That doesn't mean after 1 second. It just means as after something has happened. P1 V1 equals P2 V2. The way we do algebra, how many of these four variables are we always going to be solving for?
A.
That's not an answer. Can we ever solve for two variables in algebra?
No.
No. One. So what will we definitely, always, 100% of the time that we have this equation, what must we do with it before we can actually use it? Ty. Yeah, what do we call it? Yeah, what do we call that, though? There's a verb that we use.
Elimination.
No.
Manipulate.
Manipulate. We're always going to have to manipulate with these. Because we can't ever solve for two variables at once in algebra. Always manipulate. We're always going to have to manipulate. And I want to see that before you substitute. Always manipulate before substitute. Boyle's law is the one that doesn't have to do with temperature. We say, if temperature stays the same, a pressure on a gas increases, its volume decreases. Temp stays the same, if the temperature stays the same. That's Boyle's law. I'm going to change Charles's law to a different color. Let's use red. Charles's law. Let me show you a kind of idea. I don't know how well this is going to work with screwy glove, but let's try it. I'm going to try to make this into a balloon. This is going to be really rough. Scurvy. What? Oh! I did not think that was. Yeah, this is going to be difficult for me.
I can definitely
Oh man. I don't think I'm going to be able to do that. Does someone have tiny hands and a lot of grip strength? Your hands are not that tiny. Try it, Haley. Here, you have to really hold that. Okay, you work on that for a while. We're going to come back to that after a minute. Okay, Charles's law. Charles's law. This one, Charles's law, I remember as the one that does have to do with temperature. So Charles's law is as temperature of a gas increases, its volume, stop, okay, bye, go the other way, okay. What's going to happen? Think about balloon in your car. As temperature of a gas increases, its volume is going to do what?
Decrease. No, increase also.
Well, you guys decide. What's going to happen if we were to put this balloon, which I had here a second ago, if we were going to put this balloon into one of these, the exact same balloon, same volume of gas, into an oven and one into a freezer, what would happen to each of those?
The one's going to blow up more.
Yeah. Exactly. Just like you saw in your lab. The balloon in your lab that you put over boiling water got a little bigger, what it was supposed to, and the one you put in the ice got a little bit smaller. It's thermal contraction. As temperature of a gas increases, its volume then increases. And what kind of proportionality is this? Think about it. Don't just answer, because there are only two. I don't want you to get it wrong. Which kind of proportionality is this? Think about it and raise your hand when you know. So temperature increases, volume also increases. What kind is that? What do we call that kind of proportionality? No. Raise your hand. And that's not even one of them. They are fake. Directly. These are directly proportional. What must stay the same in this one? Temperature increase, volume increase. Which of these three things must stay the same for this to work? Pressure stays the same. For Gay-Lussac's law, let's use green. Oh, sorry, I forgot to tell you the equation. It is V1 over T1 equals V2 over T2. For Gay-Lussac's law, can you guess? Yeah. Yes, you have to memorize these equations. For Gay-Lussac's law, can you guess what this one's going to be? I'm not asking you the equation. Which two variables is this going to involve, most likely? Pressure and temperature, because those are the ones we haven't had a relationship between yet. As pressure on a gas increases, its temperature. Now this one's a little bit harder to think about, or at least usually for freshmen it's a little bit harder to think about. I wonder if you remember compressed air. Think about compressed air. It's actually a liquid when it's in the can, but let's assume it's a gas the entire time. As we release pressure on that, how would we release pressure on a can of pressurized air? Yeah, squirt it out. As we release pressure, what happens to the temperature? You know this. We're reducing the pressure in the can, and the temperature goes, Dalton? It gets a lot colder, so the temperature goes down. So as pressure on a gas increases, if we were to increase the pressure, like actually when you use a bicycle tire pump, a lot of people think that the reason the cylinder gets hot, gets hot is because they think that the plunger causes friction with the tube. That's not it at all. The gas compression, increasing the pressure of a gas, also increases its temperature. So these two are what kind of proportional? Think about it and raise your hand. Pressure increases, temperature also increases. Raise your hand if you know what kind of proportionality that is. Aaron. Directly. These are directly proportional. What must stay the same for this to work? Volume stays the same. Hey, listen. This, Gay-Lussac's law, is why when the space shuttle or some meteor is coming into the atmosphere, why the front gets red hot. People think wrongly that it's friction with the air. In fact, I hear people say that all the time. Friction with the air makes the front hot. What's actually happening is the gas, what gas? Air. The air that makes up the atmosphere. The thing coming in super fast puts an enormous amount of pressure on the air, and as that air gets squished, it gets super hot, just like when you use an air compressor. And then there's an equation for this. It's...
Do you ever tell people they're wrong when you hear that?
What? Pressure 1 over temperature 1 equals pressure 2 over temperature 2. And the combined gas law, like I said, is just like the stepchild of all of them. I don't know how a stepchild would happen with three people. I guess it can. Like, two of them are biological, and then one of them gets married to the other later. It doesn't really matter. That's not what we're here to talk about. The combined gas law is just all of them together. Combined gas law is P1 V1 over T1 equals P2 V2 over T2. I would not recommend it because some of the questions on your test will ask, which law is it that you have to use? Like, which of these 3 laws are you using here? But if you are the kind of lazy person who only wants to do one thing, you can just memorize this one, and then whichever variable you don't use, just forget it. You don't have to use it. Like if we have a question, you use this equation, but you have a question that doesn't have volume anywhere in it, you just don't write the volume one down. The equation is P1V1 over T1 equals P2V2 over T2. You still do have to memorize which law is which as far as their name and what they do, because there are questions, conceptual questions on the test like that. We don't usually do this in a video, but we have a little bit of time, and I want to make sure that you understand this. So we're going to do a couple of example problems. We'll do a balloon demonstration some other day. But let's look at, about the units. Sorry, about the units. What do you notice about these kind of variables? What's always going to happen to at least one of the units? It will cancel. It'll reduce to 1. So it doesn't really matter what kind of units we use, as long as they're the same. Hey, Carson, great job, thank you. Ramrock. Okay, I have a balloon. What happens to the volume of the balloon if I put some pressure on it? Try again. Try again. You think as I squish it, it gets bigger? As I squish it, it gets bigger. Decreases. When pressure on a gas increases, its volume decreases. When I squish it, it gets smaller. Okay? If I were to hot this up like you guys did in your lab, this is why we did that lab, what happens to its volume? It increases. And this one, if I were to let this out, we wouldn't notice it probably, but if I were to let the air out of here after Carson just spent a lot of time trying to get this sealed, if I let the air out of here, it would get, what? What would happen to the temperature? Pressure going down, the temperature would, it would be cool, it would feel cool. Dolan knows this, I can tell, almost instinctually. This happens when you let the air out of tires, even if it's very hot out, even if if it's a hot summer day, the temperature in the tires is hotter than the outside temperature, but if you let the air out, the air is still cold because of Gay-Lussac's law. This is all about the summertime, but when you're grilling, you know about when you're grilling, when your daddy's grilling. You can't touch the grill, you're a little baby. But when your daddy's grilling, and he's had the grill on for 3 hours, the propane, which is a gas, has decreased in pressure, and sometimes you'll see, in fact, very often you'll see condensation form on the propane bottle because the temperature has lowered. Sometimes you'll even see frost. On a hot summer day, you'll see frost form on the propane bottle because the temperature has lowered because the pressure, because that gas is coming out of the propane canister. Yes?
So like when you blow in your head it goes warm?
Yeah, maybe. That's probably more about Bernoulli's principle, but if we were to let the air out of this, it would feel cool.
Wait, can I do it?
No, poor Carson. He worked really hard on this. Okay, let's do one.
Think he cares?
Let's do one. Let's do one of Boyle's law. We're just going to do an example. You can use this example for Boyle's law to kind of help you understand your the other laws too. So here's one for Boyle's law. This is from page 493 if you're interested. A volume of helium occupies 11.0 liters at 98.0 kilopascals. What is the new volume if the pressure drops to 86.2 kilopascals? So we have our givens are volume 1 equals 11.0 liters. Pressure 1 equals 98.0 kilopascals, and pressure 2 equals 86.2 kilopascals. What are we trying to find? Let's read the equation again. What is the new volume? That's our actual question. So what are we trying to find?
Volume 2.
Volume 2. Which equation do we have that deals with volume 1, pressure 2, and volume 2? Look in your notes. Which equation deals with volume 1, pressure 2, and volume 2? Will? Boyle's law. The man's name is Boyle, B-O-Y-L-E, Boyle's law. And what is Boyle's law? What should we do first in every single problem? Write out the raw equation. What is Boyle's law raw equation?
V1 over T1 equals V2.
Nah, dog, you can see right here, that's Charles' law. P1V1 equals P2V2. What do I know I have to do every single time I use one of these? What am I always going to have to do? Ty? Manipulate. So what should I manipulate for here? What should I do to get V2 by itself? No. Divide by P2. We're going to divide both sides by P2. We're going to end up with P1V1 over P2 equals V2. By the way, I use this little notation here. If I think the problem is going to be difficult for myself is when I use it in real life. If I think it's going to be difficult for you, I use, what's the G probably stand for? I said it, but I want to make it clear. Given. I write down the things I am given and what variable they represent and their unit. And I write F, which stands for find, what I'm trying to find. So that helps me manipulate. What should I substitute in for P1? Let's look at the problem again. What should I substitute in for P1? No. P1. This is the other reason I write these down. 98.0, what? I have to have a unit. Kilopascal. What should I substitute in for V1? What should I substitute in for V1? 11.0 liters. What should I substitute in for P2? 86.2 kilopascals. Get out your calculator. Oh, where all my calculators went? You have them. Someone help me calculate this. I'm going to do it, and someone else is going to do it to corroborate. I'm going to type in 98 times 11, enter, divided by 86.2. What did you get?
Whatever you got.
1,078.
No. You had to press enter between the multiply and the divide, otherwise it does the order wrong.
Hold on, let me do this. 12.5. No,
12.
stop!
0.5, what? Well, let's check it out. Don't answer yet. Let's check it out. Kilopascals are going to reduce to 1 with kilopascals, leaving me with which unit? Liters. That's why I say it doesn't matter what unit these are all in, as long as they're the same. If we had kilopascals and PSI, that wouldn't work. We'd have to convert something. But in this case, they did reduce. We're left with liters. 12.5 liters is the answer. And then, last step, you ask yourself, what's step 4? Step 4 is check for reasonability. Does it make sense from what I know about Charles's law if what did the pressure do? Pressure went from P1 to P2. Pressure went down. Does it make sense if pressure went down for the volume to go up? Yes, because they're inversely proportional. So it did go up. 12.5 liters is the answer. Every single problem, write the raw equation, manipulate, substitute, make sure the units drop out, solve, and check for reasonability. Questions about how to do these? The last thing, with our little bit of time that's left, for these three, Boyle's law, Gay-Lussac's law, and the combined gas law, remember when you manipulate, if your thing you want is in the denominator, get it in the numerator first. That is so important. Bye.